Hi everybody, my name is Claire and we're going to be going over all things tree related for the final review session for 61b. So I'm going to start off with a couple of definitions. So first, we're going to be defining trees, which are basically structures that have a few rules. In general, there are a certain number of nodes and there's that number minus one edges in the tree. There's exactly one path from every node to every other node in the tree, which basically means that the tree is fully connected and doesn't contain any cycles. And here's an example right here on the screen. And that kind of leads into the definition of graphs. So graphs are pretty similar to trees, except they do allow cycles, as you can see. And a graph can have undirected or directed edges. So obviously the edges with arrows are directed, and then, and the ones with no arrows are undirected graphs. So also there's a couple different ways of representing graphs. So the first way is called an adjacency list. And basically you start with some array and every position in the array has some index that actually represents the vertex of a node in the graph. So as you can see in this graph, there's node 0, 1, 2, 3, 4, and that's the same like numbers that are in this array. And as you can see, every position in the array points to like some other list of like numbers, and those numbers basically represent the nodes that are directly adjacent to like, that position's node. So as you can see, we have this like 0 index and it represents this like 0 node, and it's pointing to a list that has 1 and 2. And that's the adjacency list of like this 0th vertex, because as you can see, 0 has an edge from 0 to 1 and 0 to 2. So those two nodes represent that, what the other node is adjacent to. We also have something called an adjacency matrix, which is also pretty similar. So as you can see, we have this like matrix, and there's like a row and a column that each again represents like a vertex in the node. And every position in this grid represents if there is a edge between those two vertexes. So as you can see, between 0 and 1, we do see this edge right here. So in the 0, 1 position on this grid, we have like true, meaning there is an edge. But for example, between vertex 0 and 3, there is no edge. So as you can see, the 0, 3 position in this grid is false, right? Because there's no edge there. Moving on, we're next going to be talking about a bunch of different traversals. And we're going to first be starting with our breadth first search traversal, or BFS. So basically what BFS means is that you're visiting nodes based off their distance to the source or your starting point or your starting vertex. So for example, in graphs, when you traverse your graph, you start with some node, and then you visit all of the immediate children before moving on to any of the grandchildren. So in this example on the right, we start with our node A, and then we visit all of its children first, so B, C, D, before going down to the next level, right? Because we're visiting the most immediate nodes before moving more downwards. And in this tree example, we kind of are going like level by level, if you can kind of see based on like the ordering. So that's why a lot of times BFS is called a level order traversal. And yeah, again, you visit the nearest level of unvisited neighbors before going deeper into the graph. Yes. And that's also pretty similar to DFS. It's again just a different type of traversals, and there's a couple of different types of DFS, but just in general, DFS is basically exploring a neighbor's entire subgraph before moving on to the next neighbor. So in BFS, we start with some node, and then we kind of go to all its neighbors before going deeper into the graph. But for DFS, we kind of start with a node and continue going further and further down into the like further down vertexes in the graph until we have some stopping point, right? Until we hit some like, node that doesn't have any more children to or any more neighbors to traverse. So we go all the way down, and then we kind of like, go back up and then do any nodes that we miss. So that's basically the basic definition of DFS. But there are two types of DFS traversals. So the first one is called our pre-ordered DFS. And then pre-ordered DFS, what you do is for each of the nodes that you're visiting in your graph, you first visit the node and then you go through all its neighbors, right? So what visiting a node basically means, a lot of times it's like you print out, what vertex or what like label that node has. Or a lot of times, during exams, they ask you to like give a list of, the order that you traversed in. So maybe visiting that node would represent kind of putting that vertex that you're visiting in your visited list, right? That for your answer in the final. But as you can see on the right, we have like a little bit of code for DFS pre-order. So as you can see, first you visit the node, which again is like printing it or adding it to the list, and then you traverse through all its neighbors, right? And this is actually directly the opposite to our other type of traversal. So it's post-order. Post-order DFS, which again is DFS, but the only difference is that now we're looking at the neighbors first before visiting the node, right? So as you can see in the code, it's basically just the opposite of pre-order, right? We're first visiting all the neighbors and then we're visiting that node. And next, we're going to be talking about SPTs, which is shortest path tree of a graph. So as you can see on the right, basically what a shortest path tree says is, oh, I'm going to give you some starting node and tell me the best path or the shortest path to visit all of like those nodes, right? So as you can see, maybe we start with this node n, and we're saying, I want to visit all these other nodes, right? I want to visit all these other nodes in this graph. So this blue would represent the SPT, or the shortest path tree, to visit all of the nodes in this graph starting from n, right? And as you can see, we're not going from T to O or O to S because I guess that's redundant in this shortest path tree. We don't need that. So that wouldn't, be part of that tree. But basically, as the name tree represent, our shortest path tree will be an acyclic kind of like representation of our shortest path. And again, the shortest path is the minimum total distance traveled between some starting vertex and any other target vertices, right? It doesn't have to be always like all the vertices in a graph. It could just be like some of them, but in this case, I guess it's hitting all the vertexes. And just in general, because it is a tree, our shortest path tree will always have the number of vertexes minus 1 edges, to be a tree. And in general, when you're trying to find the shortest path tree of some unweighted path, so in this example, all the edges are unweighted because there's no numbers there, right? There's no number connected to this edge. So finding the shortest unweighted path of some graph is just doing breadth first search. But if these edges had weights, if there's numbers connected to them, that would be finding the shortest weighted path, and then you would use these two algorithms, one called Dijkstra's and one called A-star, which I'll be going over in like a quick second, but that's how you would be finding that the shortest path tree. So next we'll move on to actually what Dijkstra's is. So what Dijkstra's says is that it will give you the shortest path tree from some starting vertex to all the other vertices in the graph, right? So given some point, it will say, oh, this is now the path to all the vertices that's the shortest. And kind of how that process kind of looks is first you would create some priority queue, and then you would add your starting vertex to that priority queue with priority 0. And then you'd add all the other vertices to that same priority queue with priority infinity. And then basically you're going to be adding and like processing vertexes that are in the queue. And kind of how it works is when you visit every vertex, you're going to look at that vertex and look at all of its neighbors. And then you're going to be writing the distance from that vertex to like all of its neighbors, right? And when you go further deeper into the graph, when you're visiting all the other vertices and looking at all their neighbors, if you see some vertex that is visiting some other vertex that you already saw, but it's like a shorter distance, you'd be updating that distance in your priority queue with that, priority number. Which is known as like relaxing the edge. And I didn't actually put an example like on these slides, but if you go to this link from the slides, it has an example that Hug put on his Google Slides. It's basically a step-by-step showing like what Dijkstra's algorithm, how it works, and how you would actually do it if you were doing it on an exam. And one thing to note is that Dijkstra's does mess up with negative edges just in general, because when you have negative edges and you add it to like, your like, I guess like distance, it's saying, oh, when you add another like edge, it could make your shortest path, I guess, like smaller than it should be. So it can like reduce the actual like distance to like all the vertexes. But yeah. So next we'll go over A-star. So what A-star does is it finds the shortest path between some initial vertex and a final vertex. So the difference between A-star and Dijkstra's is that A-star actually has some goal vertex, right? You're trying to get from point A to point B. You're not just trying to get to like every single vertex, unlike Dijkstra's. So I guess if you're trying to find the shortest path between point A and point B, something like Google Maps, right? That would use maybe A-star because you're always trying to find the shortest distance, right? And kind of how it works is it uses some heuristic to guide the path that the vertexes are taking. It uses a heuristic to guide us towards our goal, right? And then when we in Dijkstra's, we always had like some priority connected, to our vertices in the priority queue. But in this case, priority has a different definition. So our priority is defined as the distance that we've traveled already, from our starting vertex to wherever we are, and plus the estimated travel distance in the future. So the estimated travel distance to our goal, which is called our heuristic. And because we are trying to find the shortest path from point A to point B, and not just, the shortest path to every single vertex, we're actually not going to visit every single vertex, right? And here I also linked, again, another demo that Hug has that's step-by-step Google Slides of what A-star looks like. And just in general, I did mention the word heuristic, but what a heuristic in general is, it is an estimated distance between your current vertex and your goal vertex, right? So it's just saying, oh, I'm kind of going to estimate how far it is to our goal with a heuristic. And it's basically just to push us towards our goal, right? Because if you're just doing like some shortest path tree in general, you're just going to keep like, looking at like the most outer edges or the most like you're gonna look at all your neighbors right before like going to your goal. But a heuristic will be like, oh, I have like all these edges, but I know I need to go in this direction, right? Because it's closer to my goal vertex. So that's what a heuristic is. And yeah, that's basically all for the slides. Thank you so much for watching.